In this video, I'm going to show you how we can use UNet to segment nuclei with the train classifiers we just obtained before. So let me open the running notebook. Maybe it's going to be the easiest way to start it. So as before, we're going to load everything we need, and then we're going to define the parameters. So here, it's going to be similar to what we had for epithelium and stroma segmentation. So the input directory is going to be nuclei, and that's the test, where we have all the images we want to process. The classifier is the one we just trained, so the one with data augmentation, yellow as it's a file. And finally, we need to define an output directory, so I'm going to define it. If I go to UNet dataset nuclei, I'm going to define a new folder. Let's define it as results for now. All right, so I'm going to select it here, nuclei results. Okay. We have one channel, 3 classes, background, contours, and inner nuclei. We use a 256 by 256 imaging field. Now we need to decide if we want the score or the maximums of the classes. As here, we want to identify individual nuclei from these results. We better choose the score because it's going to be much more informative than just the maximum class. So I'm going to check the score, and now I'm going to run it. And as before, bunch of warnings, and then it goes pretty quickly. So we can already look at the first results. If I go there, I can then open Fiji and look at the result. All right, that's what it looks like. So if we zoom in some regions, like in here, we can see that when we have isolated nuclei, it seems to work pretty nicely. So the contours is in red, the inner in green, background in blue. So probably here we should have divided into 2 because it looks like we have 2 nuclei in here. We won't be able to identify 2 different nuclei. Now in other situation, like in here, we see that we have high values for both contours and inner nuclei, as we have yellowish pixels. So maybe we're going to be able to separate to identify this small nucleus separately from this one. So that's the next step. Now we have the classes, but we don't have individual nuclei. So here I'm going to propose one way to do it. There would be other ways as well, but it's summarized here, a small workflow. So if we start from the kind of results we have, scores, and on one hand we can threshold the background component. So if we look at the background, which is represented in blue here, if we consider all the pixels that have a very low score for background, it means that they are very much likely to be part of an object component. So that's how we're going to define so the object component is going to be the thresholded background component. So here we have all the pixels that are part of nuclei, but they're not separated. How can we separate? We can actually subtract the contours from the nuclei component and then threshold it. So if we take a threshold at 0, every pixel for which the contour has a higher score than the inner nucleus, it's going to be it's going to be used as the background to separate nuclei, and vice versa, conversely. But here maybe we want to separate a little bit more, and that's why we threshold it. So for example, we can take a threshold, so the pixels where the nucleus contour is still inferior than the inner nucleus component, but not that much, can be used to separate nuclei. Because here we really want to separate them, so maybe it's going to be better if we take a threshold that is slightly higher. So we're going to have smaller nuclei component, but by combining with the object component, we'll be able to get back the actual area. So what we do here is that from this thresholded subtraction, we can do a Voronoi tessellation. So every single pixel is associated to one nucleus, and then if we multiply this tessellation by the object component, then we get our nuclei. The only thing that is not correct there is that because of the tessellation, we have a one pixel width separation between touching nuclei, and we might want to associate this pixel to actual nuclei. So a simple way to do it is to dilate this to get the dilated nuclei. If we binarize this, then we can, by subtracting the binarization of this from the object component, extract the pixels we want to associate with nuclei, and if we multiply them by the dilated nuclei, we finally, by adding what we had here, get the final results. And I wrote an image chain macro. So if we go to plugin, so I'm gonna have to go up, so it's gonna be a pain probably. I'm gonna go slowly. If I go too fast, I'm out of the window. So I just have to go back completely at up level macro, and if I do edit, I can open one. So if I go back to a folder that was downloaded from the GitHub in codes, I have image chain macro, and there's semantic to instance, so I can open it. So it looks like this. It's a macro where you define the input, the output, and the file suffix. I'm not going to go into the details. If you're interested, you can definitely check that. The advantage here is that I put the parameters here, so the threshold on background can be really high because the background is generally very well defined. So every pixel that has a value inferior to 0.95 will be part of the object component, and then the threshold on the, so when we subtract the contours, and we can even, I would say we can definitely increase it, so we're gonna separate better the nuclei, and then I can run this. So I'm gonna select the result. So if I go back to so I'm in UNet. If I go to dataset nuclei, I just process the images that are in results, so that's going to be my input folder. And my output folder, I can go in nuclei and define, a new folder. But I'm gonna call individual nuclei. All right, select it. Suffix is TIFF with 2 F's, so then I can run it. And so as it's 32-bit float, every single time it's going to ask me if I want to open this image, and then it does all the steps. So I'm going to speed up the video so you don't have to wait for everything to be done. All right, so everything is down. So now we can have a look at the actual results. So if I go back to my folder, so I have the results from the unit, and I have the individual nuclei. Let's open one just to see what it looks like. So now you see we have different densities, so it's hard to actually see what we have. We can change the lookup table and use class B on dark, for example, but still we have so many nuclei that we have this line effect. So we're going to use annotator. It's going to be easier to look at the results. If I go back to plugins, so now I'm going to have to go down It's okay. Shouldn't be that long. And I'm gonna then open annotator, and let's see if I go to nuclei. I'm gonna open the test where we only have a DAPI. All right. And now let's load the segmentation, so the individual nuclei after macro here. And so we're going to have a better idea of what we obtained. So let me change the brightness. I'm going to increase a little bit the contrast so we can better see. So one other thing with annotator, you can remove the objects by uncheck it and then check it again. As you can see, it's already not that bad. You know, we didn't use that many images, 4 images like this. And let's zoom in. So obviously it's not perfect. In this area, in the stromal area, it's pretty good, I would say. Don't know it's perfect, just if you look at this nuclei, so they're really, again, very high density of nuclei. Segmentation is pretty accurate, I would say. Obviously, when we have this region where, you know, even by eye, it's here, you know, the DAPI quality is not good enough, so we can do a good job with by eye. So obviously we get things that are weird. Not completely wrong, you would say. It makes some sense, but not perfect. If we move to, let's try to find a more epithelial cells. You know, it's okay. It's certainly not accurate all the time, but it does a pretty good job. So I would say, you know, when you look at it, just 4 images, training is extremely fast. Just some post-processing with an image macro, and we already have pretty interesting results. So next, we're gonna see how we can train a MASCAR CNN classifier, see the results we get, and then how we can combine MASCAR CNN and UNet to try to improve a little bit the results.